Okay, can everyone hear me? Okay, hi everyone. I'm a senior researcher here at William & Mary in Dr. Kate's lab, and I'm going to be telling you a little bit about my honors research, which is, like Peter said, developing a combined approach to green gunshot residue analysis in the forensic laboratory. So, can I use the mouse? The clicker, okay. Okay, so first I'm going to set the stage a little bit. It was a Thursday in January when Scotland Yard received a call directing them to an incident at a local residence where a series of shouts, followed by a loud bang, led the neighbors to believe that the game was afoot. Upon entering the residence, the police found Professor Plum prostrate on the ground, having received 3 gunshot wounds to the abdomen. Foul play was immediately suspected. On the scene were Miss Scarlett, Colonel Mustard, and Mrs. Peacock, all of whom pleaded their own innocence, but each of whom also had a motive and an unsupported alibi. The yard booked them at the scene and pulled them in for examination and questioning. A forensic specialist was called in to help with the case involving the invisible trace of firearm discharge evidence. So, the yard knew forensic analysis of gunshot residue would be necessary for scene reconstruction and future case building. So if you're wondering what gunshot residue is, it is the particulate matter that's expelled from the gaps and openings in a firearm during a discharge event. It's released as a plume or a cloud of materials that have been vaporized during the chain deflagration that results from the series of mechanical and chemical interactions that follow the pull of a firearm trigger. So it triggers a rapid buildup of temperature and pressure within the firearm, resulting in the vaporization and subsequent rapid release of these particulate matters that are components of the primer, bullet, and cartridge case, and other firearm components. And these then rapidly condense and settle on surfaces in the vicinity of the discharge. So this can be things like the hands, hair, skin, and clothing of the shooter, which gives it a very direct relationship with firearm discharge events, which means it can be collected and used as evidence in a case of a suspicious discharge. So there was a problem. The forensic scientist they called in was trained according to standards set out by the Organization of Scientific Area Committees for Forensic Science, or OSAC, which established scanning electron microscopy, or SEM-EDS, scanning electron microscopy with energy dispersive X-ray spectroscopy, which is SEM-EDS, as the standard method for the analysis of gunshot residue. It relies upon the detection of characteristic heavy metal containing particulates as the inorganic components of collected residues. But manufacturing standards for ammunition producers have recently changed to address concerns over the continued exposure to heavy metals, especially because they become vaporized during the discharge of a firearm. And this has led to a change in the formulation of gunshot, which we're shifting towards green ammunition, which omits these heavy metal elements in favor of substituting them with more environmentally omnipresent elements. So this means that the samples that were collected didn't adhere to the expected standards, and the forensic scientists couldn't conclusively identify whether GSR was actually present. But they have my number on speed dial, so I'm gonna fix it. So the starting point for this project was the redevelopment of existing profiles for the classification of the inorganic components of gunshot residue, known as IGSR, via SEM-EDS. This redevelopment was done in the context of samples containing only green GSR so that these developed profiles could be applied alongside other analytical strategies developed in later project stages. Samples were collected and stored using these SEM-EDS compatible forensic sampling kits. They consist of a glass vial made airtight when capped with a flexible lid to which a 12mm aluminum pin stub affixed with black carbon adhesive is attached. During the sampling process, GSR particles are collected by dabbing the surface of the adhesive across the palm and the back of a volunteer's hand and then up their forearm. And then we collected them following an internal review board approved protocol, which involved sampling from the hands of police officers during a routine firearms recertification training period at a local firing range. And we certified that all ammunition used was of the green variety, so in sampling and then in later evaluation, we could know that there was at least some quantity of green GSR present. So after analyzing many samples, we were able to compile what we saw as a more accurate morphological SEM and elemental EDS profiles of the heavy metal-free GSRs we were looking at. This provided a more reliable basis upon which we could begin to characterize the inorganic components of RGSR samples, and the key details seemed to be noting that the particles we were looking for tended to sparkle against the background because this wasn't something that the OSAC standards noted, and it seemed to kind of draw us to particles that were likely components of GSR. So these were things that were high in metal content, not heavy metal content. That's important. So despite the fact that this provided a basis upon which we could begin to characterize our samples, there was a degree of arbitrariness to it. We're basically still kind of choosing the particles we're looking for based on this fact that they're kind of sparkling against the background. So there was definitely a need to develop something that would be more objective and less subjective. So we moved on to developing GCGC for the analysis of the organic components of gunshot residue, or OGSR. The hope is in that developing both methods, a combined approach to the analysis of both IGSR and OGSR may be established and allow forensic analysts in the laboratory to create a more complete and comprehensive profile of the green GSR samples that are becoming increasingly common in their laboratories. In establishing a more complete profile, analysts would be stabilizing the credibility of their analyses in the courtroom, therefore supporting the viability of GSR as forensic evidence. So I'm not really going to go through this a lot because we know what 1D GC are, and we've talked a lot about GCGC during this conference. But the major differences between 1D GC and GCGC are the addition of a modulator and the addition of a secondary column, which in GCGC provide additional degrees of separation. So for applications like forensic analysis, especially in the context of GSR where we have extremely complex samples, GCGC may provide a distinct advantage to a forensic analyst in the laboratory because those additional degrees of separation could help to separate components that are nitroaromatic compounds that have kind of similar structures, or there are many constitutional isomers of things like dimethyl phthalate that we want to see, but we may not be able to see kind of separated in only one dimension. So, as with SEM-EDS, national standards organizations have also published guidelines for the analysis of OGSR by one-dimensional GCMS. For the purposes of this study, we used a liquid method for the extraction of OGSR adapted from the OSAC standard for the collection and analysis of OGSR by GCMS. And in this method, it was specified that the forensic sampling kits that I showed earlier were what was used for sampling because they're the typical field convention. So, samples were extracted in methanol, evaporated to dryness under nitrogen, and then reconstituted and transferred to analysis vials compatible with the Pegasus BT40 GCGC TOF-MS, which is time of flight mass spectrometry, system provided by the LICO Corporation that was used for this project. Between transfers to vials, a series of steps involving sonication and vortexing were taken to ensure that we extracted the maximum concentrations of analytes that we could. So we developed this method based on the OSAC methodology, but we wanted to compare it to something that we were seeing in relevant literature. So in the topmost chromatogram, we have a sample extracted according to the in-house method that we adapted from that OSAC standard. And in the bottommost chromatogram, we have a GSR sample that was extracted using the method adapted from literature. So it's kind of visible in these chromatograms that our in-house method not only seemed to extract more compounds than the one adapted from literature, but also seemed to extract higher quantities of the things that both picked up. Because the peaks in the topmost chromatogram are more obvious, more intense, so we can assume that we're getting more of that stuff that's kind of following the same pattern in both chromatograms. Additionally, the in-house method, when compared with the literature method, extracted a higher average number of peaks, and for the background skin matrix compound in hexadecanoic acid and the known OGSR contributor and nitroaromatic compound diphenylamine, it showed higher average peak areas when averaged across 4 samples extracted according to each protocol. So we were led to determine that the method that we developed in-house, adapted from the OSAC method, was what we would use for further extraction because the combination of higher peak areas for target analytes, the extraction of more analytes, led us to kind of conclude that this would be suitable for further OGSR analysis. So after identifying the effective sample extraction procedure, we moved on to optimizing the GCGC program used to analyze samples once they had been injected. An oven temperature program had been developed during previous experimentation based on literature sources and the physical properties of known OGSR compounds. And then hydrogen was chosen as the carrier gas after some initial analyses proved it to improve compound visibility and resulting chromatograms. So the initial samples run on helium were kind of compressed, and we couldn't really conclusively identify the components of OGSR that we were looking for, so we decided to stick with hydrogen moving forward. But what we were left to optimize was the inlet temperature for analyte desorption onto the primary column after injection and the modulation period. So we started with comparing inlet temperatures. We chose 170 and 200 degrees Celsius to compare because we needed the temperature to be high enough so that the analytes we were looking for would volatilize, but we were concerned whether 200 degrees Celsius was too high and we were getting some analyte destruction. So the chromatograms are pretty similar visually, but data processing did show that the 170 degrees Celsius temperature led to the extraction of more analytes than the 200 degrees temperature. But for target analytes, the ones relevant to gunshot residue, such as ethylene glycol dinitrate, which is synonymous with nitroglycerin, and diphenylamine, they appeared at lower peak areas or not at all when the temperature was 170 degrees Celsius. So for the specific application of analyzing OGSR, we stuck with the 200 degree inlet temperature. And then the final step in the method optimization was the comparison of modulation periods, which is the length of time in which analytes eluting from the primary column are trapped into the modulator before being reinjected into the secondary column. So it's essentially the size of a sample plug that moves between the two columns. So we chose 3 generally standard modulation periods to compare, which were 2 seconds, 2.5 seconds, and 3 seconds. And here we have the chromatograms resulting from the analysis of a GSR sample on a 2-second modulation period and a 2.5-second period. So we see this problem called wraparound, which is where in the 2-second period, where a analyte can't fully come out in one modulation period. So this led us to determine that 2 seconds might be a little too short, and 2.5 seconds maybe would be around the right time. So we wanted to go to something maybe a little bit longer to see if this was the case. And we had the opposite problem when we did the 3-second modulation period, where we have all of this wasted chromatographic space and all of the compounds eluting are compressed into the bottom half of the chromatogram. So this led us to conclude that we would use a 2.5-second period moving forward in all chromatographic programming. So this is the summarized, final, optimized GC, and MS programs used for the analysis of GSR in this project. Aside from the inlet temperature and modulation period, which I just discussed their optimization, the remaining parameters were adapted from literature or assigned per manufacturer recommendation, and this program is what's used for all further data collection and analysis in this project. Okay, following the program development and optimization, we moved on to validating whether analytes known to contribute to OGSR and resulting chromatograms were appearing at consistent retention times. So for this portion of experimentation and method development, we analyzed a selection of a 7-component phthalate standard, a 12-component nitroaromatic mix, a standard of nitroglycerin, and a 9-component gun surveillance standard, which was composed of a lot of nitroaromatic compounds. So for each of the following standard analyses, like I said, we used that same GC program that I talked about the optimization of earlier. We had the phthalate standard first, and for most of these, the dilution was a 10 ppm working, the working solution was a 10 ppm serial dilution of the original standard. So a lot of these came in 1,000 ppm concentrations of each analyte. So from this, we were able to achieve successful identification of all 7 analytes, all of which appeared in a retention time window ranging between about 700 to 2,000 seconds in the first dimension and between 1 and 2 seconds in the second dimension. As you can see, the peaks were well resolved and distinct. And then I kind of have zoomed in on a certain retention window here, which is why I was talking about the ranges, because this is where all the compounds eluted. So keeping this same window, comparing it to an actual GSR sample, we have confirmed identification of at least 3 known OGSR components. So here they appear at lower concentrations relative to the background, but that was expected. And this is the 12-component nitroaromatic mixture, and again, we were able to conclusively identify all components. And this was especially significant because it validated that compounds such as TNT, DNT, and nitrotoluene, which are common components of explosive and propellant mixtures, were not only visible, but well resolved from similar compounds using our method. So in 1DGC, I'll use this. Okay, which one's the laser? Thank you, okay. In 1DGC, this mass of compounds in the middle might not be so well resolved. We might see it kind of coalute, which is kind of showing that GCGC has improved the visibility of target compounds for OGSR. And then we identified nitroglycerin, and this was regularly identified in preliminary GSR analysis, so we'll be using these retention times to kind of verify its identity moving forward. And then we analyzed the gun surveillance standard last, which wasn't quite so successful, and we were able to identify 7 out of 9 of the components, but 1 component appeared as a part of the column bleed, and then 2 components, phenazine and benzothiazole, that were not a part of the standard appeared alongside them. So we need to give this one a little more attention, but for a preliminary analysis, we're off to a pretty good start. So in conclusion, our work so far has culminated in a fully developed strategy for the analysis of green IGSR using SEM-EDS, which has since been used in all analyses, an optimized liquid extraction protocol used to prepare samples of OGSR collected using forensic sampling kits for analysis on GCGC, a GCGC analysis program optimized to capture data on OGSR components, and we have verified the identities of relevant analytes in the chromatograms using the standards that we ran. So, in the case of the invisible trace, Scotland Yard and I were able to point a finger at Miss Scarlett. However, though we were able to implicate her in the eyes of all involved parties, it remains to be seen whether our analyses will stand up at her trial. So Federal Rule 702 governs the admissibility of expert witness testimony in the courtroom, and it states that it must rely upon the admission of sufficient facts or data and the product of reliable principles and methods. So though the method we've developed thus far works enough to confirm whether GSR is present or absent, and worked enough to confirm that Ms. Scarlett probably did it, we want to continue with more optimization testing, including the comparison of sorbent-based extraction methods to the developed methanol-based liquid extraction strategy, and we want to verify these analyte identities further through obtaining retention indices. And we hope that in doing all of this, we will create a method that can be adapted and put into the forensic laboratory and really help forensic scientists in the age of green ammunition more conclusively identify what's present in their samples. So with that, I want to thank Dr. Kate, and I want to thank my lab mates for listening to me practice this presentation maybe 10 times. With that, I'll take any questions.